Hey, it's Mr. Shrum, and I'm going to look at spectral lines today with you. And here's the introduction. Astronomers can determine the composition of stars and other astronomical objects that are thousands of light years away. And shopkeepers hang bright signboards in different colors to make their shop stand out at night. Investigators identify unknown substances found at crime scenes, and they all use spectral lines of an element to complete these actions. Each element emits a unique frequency of light that is known as its emission spectrum. This light frequency is unique, and it's similar to how a fingerprint is unique to humans. So light has a light print, if you will. These samples can be substances from crime scenes or rocks from space. Because of this property, spectroscopy, that's that word, is an important branch of study in chemistry-related fields like forensics, medicine, and astronomy. Quantum jumps. When electrons absorb energy, they jump from low to high energy levels. And when the electrons in an atom are located around the nucleus at a specific quantum energy level, this energy level is called the ground state of the electron. And as the distance of the electron from the nucleus increases, the energy level also increases. If an atom of an element is exposed to a source of energy like light, the electrons in the atom absorb that energy and then they jump to that higher energy level. And they call this the excited state. Electrons can't stay excited like most human beings. You may get excited, but to be in that state, it takes a lot of energy. So you'll eventually come back down. And when these electrons come back down to a lower energy, they emit a photon, a energy in the form of electromagnetic radiation. These jumps are known as quantum jumps between energy states. The range of electromagnetic radiations emitted by an element makes up the spectrum of the element. You might have seen the spectrum of sunlight when it passes through a prism. It looks like the rainbow. You know that electromagnetic radiation has different frequencies. White light is made up of all frequencies between infrared and ultraviolet. During electronic transitions, electrons emit specific frequencies of radiation that depend on the atom. Each element will emit only certain sharply defined lines of colors. The line spectrum emitted by an element is called its atomic emission spectrum. The unique emission spectrum of each element is useful in identifying the element in unknown samples with the help of a spectrometer. Other sources of energy, like electricity, can also excite electrons and cause them to be excited to the next level. The ground state, where it initially starts off, is called n equals 1. And then as it goes up each level, we say n equals 2, n equals 3, and n equals 4, and so on. The larger the distance between the ground state and the energy it's excited to, the more energy it has and the more it will emit once it comes back to a lower energy. Here's the activity. Let that load. Here we go. Okay. And let's go back to the instructions. Click fire electron to fire an electron, of course. In this, you will see energy transitions. We'll just go with one, I guess. Yeah. Okay. Click fire electron to fire an electron at the atom. Ta-da. Okay. You can choose the continuous option to bombard the electrons continuously. Yeah, we'll just do that. Oh, whoops. Oh no. Wow. Okay. Okay. By default, hydrogen is selected. You can select other elements too. And the panel on the right also shows the changing energy levels of the electron, the atom, as electrons hit it. Select the spectrometer checkbox to observe the wavelength and colors at which photons for each atom are emitted. You can also select the run in motion or run in slow motion option to observe the effect more clearly. The one atom tab places one atom of the selected element at the center, while multiple atoms place several atoms. Okay. Okay. Part A, select the run in slow motion checkbox and fire an electron. Note what happens to the energy level on the right when the electron hits the atom. Note the change in electron energy when a photon is released. Explain why photons are released when a charged electron strikes an atom. All right, we're gonna run in slow motion because it's a little fast right now. So wham. Here. Oh, okay. So we have it. Here's the ground state. It's excited, and then it comes back down. And once it comes back down, it emits a photon. Select the single option from the electron production and fire electrons at the atom. Try this with all the types of atoms. You'll observe that in some cases, the atom releases more than one photon. Why do you think that happens? Okay, here we go. There's hydrogen. Let's do mercury. Well, it seems like it's excited and it goes to certain levels. And sometimes it releases two. There it is. And it goes back to the ground state. Okay, so here we go. Each time an excited electron transits from a higher energy level to a lower energy level, it emits a photon. In certain cases, electrons come back to the ground state in 2 steps. So 1, 2. And if that's the case, it releases 2 photons for each step. Part C, select the multiple atom. Oh my goodness. Okay, here we go. Now select hydrogen, run the experiment. Note the colors and wavelengths of the photons shown in the spectrometer readings. Do the same with neon. How do you differentiate hydrogen and neon using the spectrometer readings? Okay. Spectrometer. Wait. Hydrogen. Yeah, there we go. Oh, wait, run in slow motion, probably too. Okay. Now select hydrogen, run the experiment, note the colors and wavelengths of the photon shown. Do the same with neon. How do you differentiate hydrogen and neon? All right, so we see with hydrogen, a specific frequency of photons being seen. That's hydrogen. Now let's do neon. Neon, I believe. Yes, yes. Okay, neon. So this is a totally different, we're seeing totally different colors of photons, frequency. Okay, cool. Hydrogen, totally different. Excellent. You can distinguish them based on the atomic spectra, and that's shown on the spectrometer. Hydrogen consists of light having wavelengths between 410 nanometers to 660 nanometers in the visible light range. They're purple, dark blue, sky blue, and red. Hydrogen and neon can be differentiated based on the wavelengths and colors of light they each emit. From the multiple atoms tab, select the continuous option from the electron production control and also select the spectrometer and squiggles options. Now run the experiment and then make observations comparing the behavior and results of neon and sodium. Both neon and sodium show yellow and orange colors. How can you distinguish between these two elements? Okay, so neon, sodium, and neon. And that's that. And then neon. Well, I mean, it just looks totally different. Why would it? And yes, there's orange and yellow, but it's pretty easy to tell them apart. Okay, so their emission spectra in the visible range are not the same. In addition, sodium does not emit any light in the infrared range. This property can be used to distinguish the two elements. Each emission spectrum of the element is unique. Energy and radiation. According to the classical wave theory of light, light is a continuous electromagnetic wave that has no mass. This theory assumes that the energy in light waves is emitted continuously and can be absorbed and emitted by matter in any quantity. This theory was adopted and accepted until the end of the 19th century, so the end of the 1800s. At the beginning of the 20th century, the beginning of the early 1900s, scientists could not explain the result of certain experiments with this wave theory. When Max Planck was studying light emitted from heated solids, he observed that as energy in the form of temperature was increased, the color given off by the solid changed from red to orange and finally to white. However, there was no increase in the intensity of brightness, intensity or brightness of the light as would have been expected. So he needed a little more to explain than what the wave theory provided. He proposed a theory to explain what classical wave theory could not explain. His theory stated that an atom will not absorb or emit energy continuously, but only in very discrete packets or units of energy called photons. The frequency is represented by the Greek letter nu. Therefore, the energy of a photon is given by E equals h times nu. H is Planck's constant, 6.626 times 10 to the negative 34 joules seconds. And if we substitute C divided by the wavelength, which is using this equation, you can plug that in for nu, E equals h times C divided by wavelength. And then we get E equals N, which is the energy level. So E equals N times H times nu. And that's the discrete amount of energy per packet. When a specific electron transition occurs in the hydrogen atom, a photon with a wavelength of 21.106 centimeters is emitted. This 21 centimeter line of hydrogen is in the radio spectrum and is extensively used in radio astronomy. Let's calculate the energy change associated with this particular electron transition for hydrogen. Any change in the energy of the electron or the hydrogen atom will be equal to the energy of the photon it emits. We know that the energy of a photon is given by E equals h times nu. H is Planck's constant, nu is the frequency. Frequency equals the speed of light divided by wavelength. So if we plug all that in, this is what you get. Now we have more practice of calculations. H is this number, Planck's constant, and then C is 2.998 times 10 to the 8th meters per second, the speed of light. And we're given the wavelength. Calculate the energy. We're going to use those equations, plug in the numbers, and it's going to be straightforward. So we have nu equals the speed of light divided by wavelength. The energy equals Planck's constant times nu. And since nu is equal to the speed of light divided by wavelength, you just plug in those numbers. And you get 5.2276 times 10 to the negative 19 joules. Joules because we're talking about energy. Part B is practicing the other equation, and we're jumping from the energy level 4 to 2. And a photon of energy 4.165 times 10 to the negative 19 joules is released. Calculate the wavelength. All right. So we're going to use those equations, rearrange them, and then plug in what we know. Nu equals the speed of light divided by wavelength. E equals Planck's constant times the speed of light divided by the wavelength. So you're plugging in and then rearranging it where you're calculating the wavelength. And you wind up with 4.77 times 10 to the negative 7 meters. The frequency is 4.77 times 10 to the negative 7 meters. Which of the following is the change in energy of an atom emitting a photon of wavelength 4.35 meters? Well, I wonder why you can't just show you the correct answer from this one. Okay. But you would just calculate that using this exact same method. Okay. Thanks. Okay. And lastly, we're going to look at emission and absorption lines. And these are what those look like. You now know that every element has a unique atomic spectrum. In fact, an element can emit 3 types of spectra: continuous, an emission spectra, and an absorption spectrum. So emission is what the light is, or what you can see being emitted from the elements. And then this is what it actually absorbs, okay? And it absorbs everything that it's not emitting. So these are opposites, you see. The spectrum emitted by electrons returning to a lower energy level from a higher one is called the emission spectrum. And therefore, this spectrum is called the line spectrum too. So the lines, you get the line spectrum, the emission spectrum. Alternately, when white light is passed through a cool gas, the gas atoms absorb specific frequencies of light, and their electrons go the other way from low energy to high. The resulting spectrum appears as dark lines against a continuous spectrum. These dark lines are the element's absorption lines or absorption spectrum. Absorption lines for an element appear at the exact same frequencies as its emission lines. Here, the hydrogen spectrum consists of different series of spectral lines in different ranges of electromagnetic radiation. The series of lines, or line spectrum, produced depends on the lower energy level involved in the electron transitions. You've seen in the simulation of atomic spectra that electrons in the excited state may return to the ground state in more than one step. The different spectral series of hydrogen arise because of these like 2-step transitions. These lines were first observed by Theodore Lyman when a hydrogen atom jumped from higher energy levels to the ground state. The transition of electrons from higher energy levels to n equals 2 generates spectral lines in the Balmer series, observed by Johann Balmer in 1885. This series is in the visible range of the spectrum. When electrons move from higher energy levels to n equals 3, the Paschen series is produced, first observed by Friedrich Paschen. I may not be pronouncing his last name correctly. Shoot. I've only seen it in writing. But those are in the infrared range. So depending on which energy level is being jumped from and to, you will see different lines. And the spectral lines of hydrogen have applications in a variety of fields. In astronomy, spectral lines in the radio spectrum of hydrogen are useful in observing objects that are not in the visible spectrum. Most objects in space emit radiation at radio frequencies, and detecting these frequencies with radio telescopes can help in imaging and analyzing these celestial objects. Much of our knowledge about the universe is based on observing hydrogen spectral lines in the ranges of visible light, radio waves, and X-rays. Hydrogen lines of certain frequencies are also used to measure the salinity of ocean surfaces and moisture content of soil, which are very useful for studying the water cycle and predicting climate conditions on Earth. In summary, astronomers, crime investigators use spectroscopy to identify unknown elements by their atomic spectra. This is their light or electromagnetic fingerprint, like a light print. An absorption spectrum is generated when an electron absorbs energy and jumps to a higher energy level. When this electron returns to the energy level that is lower, it releases photons in an emission spectrum. The abrupt movement of an electron between energy levels is known as an electron transition. And we can use this equation, E equals h times nu. H is Planck's constant, nu is the frequency, and E is the energy. And remember these three spectra: a continuous one, emission, and absorption. Continuous is all wavelengths. Emission and absorption spectra are unique to each element. All right, that's that. All right, well, thank you guys. And if you have any more questions, be sure to message me. But until next time, have a good one, and I will see you all next time. Bye-bye.